Alright, this is lecture 4. And in the previous lecture, lecture 3, after finishing this short lecture, you have achieved many things. Now you can log in into our exercise workstation and start some useful programs: VI, Emacs, Ångströmcraft, and GDevice. Of course, when you type Ångströmcraft or GDevice, you just get a trivial result, but it's okay. Now you can start them. So let's just see what happens from now on. But today's lecture is not for Ångströmcraft or GDevice, and today's goal is the visualization. For both Ångströmcraft and GDevice, the simulation results are saved in the CGNS file format, Computational Fluid Dynamics CFD General Notation System. So today we will learn how to visualize a CGNS file containing physical solution. Type ParaView in the terminal. ParaView is an open source visualization program, and fortunately it supports the CGNS file format. So as you can see here, it can make a very beautiful graph out of computationally generated data, but we will use it for our own purpose: semiconductor device simulation and visualization of certain structures. So now let's start an example of a nanowire transistor. This example is prepared by Dr. Kwang Lee during his PhD study. And as you can see here, it is a quarter of the entire structure. Here, gray region is corresponding to the silicon. Here we have a square silicon, and it is surrounded by this red colored silicon dioxide. So we have silicon dioxide, and somewhere here we have gate and source and drain. So now I will just show you how can we visualize this structure and see some physical quantities out of it. Okay, this is my terminal, and now we can just type ParaView, and we have to specify the input file name, the CGNS file. So let me just say that this is eq1.cgns. So eq1 means that the first equilibrium solution, but the name is not that important. You can change it. But when we start this ParaView, then we will see this one. So as you can see, this part is for visualizing our structure, but although I type ParaView eq1.cgns, there is no structure at all. So in this case, you can see that it is not checked. So eq.cgns is here, but it is not selected. So please just click it, then you can now have a look at this structure. What is it? By click a certain point and drag the mouse, now you can rotate it. So it is much easier than it looks, so you can just have a look at this one later by yourself. Anyway, now you can see certain nano load, and what is it? This one just looks just a single body, but no, this is not the case. When you have a look at this multi-box inspector, you can see several things are here: semiconductor, insulator, source, drain gate. The name itself is not fixed, so it is just determined by user, but meaning is anyway, in this structure, we can introduce many different parts, sometimes called the regions. And source, drain, gate are just two-dimensional structure corresponding to, for example, just contact. And where can you find gate? Yes, this is the place of a gate. So now we have, for example, here we have a source, and here we have gate, and finally, now we have drain here. I see. So in this case, Z direction is the channel direction, and now we have a gate. And other two parts, semiconductor and insulator, are volume components. For example, if we just select the insulator, now this insulator is covering this central semiconductor part. So now you understand this is a quarter of the nanowire transistor, and here we have a channel region, and it is surrounded by oxide region, and it is finally covered by this gate contact. So now you understand the situation. And how about the solution? So it just shows only, well, just shows structure. However, usually what we wanted to know is physical quantities like electrostatic potential or electron density, hole density. How can you select this one? Okay, I will explain it from now on. Before talking about this one, by checking or unchecking this box, you can just remove, for example, this insulator region from visualization, or, for example, semiconductor region from this visualization. So you can easily do that. And now go to the property, and you have several already existing data fields, and you can easily recognize the physical meanings of these quantities. But for a while, just to have a look at one typical quantity called as electrostatic potential, so you can check it. Then nothing happens because just selecting electrostatic potential doesn't make the immediate result. So you have to this apply button. Then now your selection will be effective. So when you click apply, then yes, we just see these two different colors, and electrostatic potential is constant over channel region, so it's not. So when we scroll down, then you can find the way of coloring. Right now, these two colors are corresponding to different blocks, so different regions, semiconductor or insulator. So it doesn't show the physical quantities like electrostatic potential. But when you just open it, then you can find then now electrostatic potential can be selected. So when you just click it, then now instead of this block number index, now you can see the physical quantity electrostatic potential. Well, here we have a red one. Usually in this convention, red one is more positive and blue one is more negative. And now you can see that due to the action of gate contact, this part shows a relatively high electrostatic potential. Why don't you just remove this insulator? Then now you can see that although the electrostatic potential at the gate contact itself shows higher values, but compared with this one, This one is just a moderate value. Well, this color graph looks beautiful. However, it is difficult to see whether this is the really meaningful difference or not. So in order to check that one, let me just make the plot along a certain line. So we can do it in this paraview. But before doing that, let me just show you once again, rotating. And another one is you can select this viewpoint. For example, this one is vertical to the x-axis, and these two are corresponding to the one vertical to y-axis, and this one is corresponding to the direction vertical to the G direction. Of course, you can just make the rotation again. And another one is, now you can see that this one can be zoom out and zoom in. So how can you do that? It is quite simple. In your mouse, usually you have a mouse wheel, and by just changing its view position, now you can zoom in or zoom out of your structure. I'm not quite sure what will happen if you have a different mouse types, but mine has two buttons and one wheel. In that case, it looks just a perfect conventional way. Okay, so now let's come back. I have covered the zoom in and zoom out, and ready. Physical quantity, electrostatic potential is shown here. But maybe you can ask me this question. I don't want to have a look at just the electrostatic potential. I also wanted to show the electron density. Then where can you find the electron density? That is reserved as E density. So just to click it and apply. Then now you can see that, oh, here we have another physical quantity to be drawn. So by clicking, then now you can see that things have been changed a little bit. And also, well, here, so it is not shown in this limited view, but now, well, the values are changed quite a lot. It is corresponding to 10 to the 20 because this is the electron density, not a potential. Well, in this case, let me just draw a one-dimensional graph along a z-axis. So, this is the channel directional quantity. How can you do that? So, you can find it here. So, plot over line. When you click it, well, you can just have a look at a single arrow, and this arrow can be actually controlled, the initial point and final point, and you have also predefined ones which are aligned x-axis, y-axis, z-axis. Why don't you just click this z-axis one, then you can find that, okay, this one is now following this z-axis. Of course, you can see its x position and y position looks a little bit strange, so you can just select it by manually changing. But right now, I will just accept this one and say apply. Then what will happen? Only when you click this apply, it will generate a certain physical quantity along that given line. And okay, so now you can see here a certain line corresponding to this one. This one, just the red one, shows the electron density, and its value is 10 to the 20 in this example. source and drain are doped with 10 to the 20 per cubic centimeter. So that's the reason why we have this value. And in this central region, then we have a relatively lower electron density. So like just 4 point something times 10 to the 19 per cubic centimeter. So this is the channel region, source, and drain. Of course, when you have a look at, for example, this panel, then you can find that both of electrostatic potential and E density are currently being displayed. But E density has orders of 10 to the 20 per cubic centimeter, and electrostatic potential is just in the range of a few volts. So that is not shown here. So if we unclick it, then now you can see that clearly this is the potential, and potential is about 0.5 something. Okay, now we have done the plot of a line, but still we need a little bit more. Right now we have just to uh, see the surface of this entire structure. But sometimes we want to make this cross-sectional view. Then how can we make this cross-sectional view for our system? When we select this clip, then now you can see that, oh, what is it? So this red plane just shows the plane we will make for clipping. So let me just do it once again by clicking G normal. And also you can just yes, change the position of the actual clipping. But anyway, select anyone here. Then let me just click apply. Then now you can see that by viewing it, so now you can see that the electron density is highly populated here, the corner of our nanowire, because here we have a highly concentrated electric field, and we have also other parts, channel part, having relatively higher electron density, and we have a relatively lower electron density. So this is quite much acceptable when we consider semi-classical simulation. Of course, if we consider other one or with quantum potential, then that will show a little bit different behavior. But in this example, it's completely okay. Okay, so this is the result of clipping, but let me just come back to our original structure. So you can easily select or unselect these ones. Yes, quite easy. And finally, I would like to show you how can you do certain ruler generation. So let me just delete it. Okay, now we have it. How long is it? How long is this structure? Then it is not certain. So here you can see you have a ruler one. Just to click it, once again you will get certain line, but we wanted to measure the x or z directional length, channel directional length. So just to click this z direction. So now you have a very long line, like minus 0.5 or 0. So let me just say, where is it? 0. Now you can see that this one is corresponding to 0. So then how about 0.1? No. Then how about 10 to the minus 3? Oh, now we have just quite short. Then how about just number 10 to the minus 2? Okay, so now we have 10 to the minus 1. Oh, this is too long. So you can easily understand the size of this system is more or less corresponding to 0 point something. So 3, 4. Okay, so maybe 0.045. Okay, now you can see that this structure has the length scale along this g direction about 0.045. What is it? This length scale is given as a micrometer, and therefore its 1,000th is corresponding to nanometer, and this number is corresponding to just 45 nanometer. So let me just have a look at this one. In this case, we can select gate, and now we can see that here and there. Oh, we can find. Oh, the ruler is just no apply. Okay, so now you can see that this one shows the ruler corresponding to 45 nanometer, and here we have just gate length is 1/3 of it. So yes, so maybe okay. So when you have a look at this one, this is 15 nanometer, 15 nanometer for gate, and 15 nanometer for this another drain part. Okay, so I think that I have covered many capabilities in this example. Selecting or unselecting a file, and selecting unselecting regions, and rotating viewpoint, and yes, 3D 2D selection can be done by this one. Then it becomes 2D graphs, and it becomes a 3D graphs. When you make it 2D, then changing it just to translation move this one structure. So let me just come back to this 3D and zoom in, zoom out, and you can select the quantity of your interest, and you can visualize it, and also plot a line or clip slice. Oh, I skip slice, but it is quite similar. And also you can make the ruler. So I guess that it is quite good to have this paraview expertise. Then after that, now we have covered our example, and let's go to our homework number 4. Up to now, you have seen the example of EQ1.CGNS. It was a quarter of a nanowire. Our TA will give you a new CGNS file. What is it? It is not known to you. And please take a screenshot of its various regions. Then describe the structure in the physical size or some material composition, because region names shows some materials or some hint for its roles in the structure. So after that, please try to guess what this structure is. That PDF file report will be for homework number 4. Thank you, and see you later in the offline lecture in lecture 5. Bye.